Hello, and welcome to this online lecture. My name is Patty Kokish, and today we're going to be covering Chapter 10 from your online Math 200 class. So Chapter 10 is all about hypothesis testing regarding a parameter. So we're going to start with section 10.1 because we haven't done hypothesis testing before. So the first thing we want to do is actually talk about the language of hypothesis testing. So the first objective is to be able to determine what's called the null and the alternative hypotheses. So you probably have heard of a hypothesis before, probably in science classes, and it's just a statement regarding a characteristic of the population. So in this particular chapter, we're going to look at hypotheses regarding a single population parameter. So let's look at some examples of claims that are regarding a single population or a characteristic about a single population. So in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So in a minute, we're going to write the hypothesis test for this, but this is an example of something where we're looking at the characteristic of a population. Here's another example. According to a study published in March 2006, the mean length of a phone call on a cellular telephone was 3.25 minutes. A researcher believes that the mean length of a call has increased since then. And then finally, using an old manufacturing process, the standard deviation of the amount of wine put into a bottle was 0.23 ounces. With the new equipment, the quality control manager believes the standard deviation has decreased. So the first example talked about a proportion because we had 62%, okay? The middle example talked about a mean because it was an average of 3.25 minutes. And the last one talked about a standard deviation. We're going to focus on hypothesis testing for the first two types of examples, where we have population proportions and population means. So one kind of word of warning or caution is that we test these types of statements using sample data because it's normally impossible or very impractical to actually gain access to the entire population. So if population data are actually available, there isn't any need for inferential statistics. But as you know, if you want to find something out about the population, you can't possibly ask everyone. It would be much too time consuming and much too expensive. So you have to take a sample in order to infer back on the population. So hypothesis testing is a procedure that basically allows us to do this. It allows us to take sample evidence and probability and test statements regarding the characteristic of one or more populations. So there are several steps involved in hypothesis testing, and this you don't need to really memorize this, you just need to understand it. The first step is to actually make a statement regarding the nature of the population. And then you go ahead and collect evidence, which is going to be your sample data, in order to test the statement. You analyze the data to assess the plausibility of the statement. And you make some kind of conclusion, which isn't listed here, but that would be part of the analyze portion. Okay, so the null hypothesis, denoted H naught, is a statement to be tested. The null hypothesis is basically a statement of no change, no effect, no difference. And we just assume it to be true unless evidence indicates otherwise. Now, the alternative hypothesis, denoted H1, is a statement that we're trying to find evidence to support. So in this chapter, there are basically three different ways to set up the null and the alternative hypotheses. There's first a two-tailed test, okay, which is testing basically equals versus not equal. So your null hypothesis is going to be that the parameter equals some value, and your alternative hypothesis is that the parameter does not equal that value. Equal versus less than is going to be a left-tailed test. So you'll see for each of these, your null hypothesis is set up the exact same way. It's your no change hypothesis. So we're always going to have H naught being the parameter equal to some value. You have a left-tailed test if you say that the parameter is less than some value, and you have a right-tailed test if you say that the parameter is greater than some value for your alternative hypothesis. So in other words, the null hypothesis is just a statement of status quo or no difference and always contains a statement of equality. So you're always going to have the same null hypothesis, parameter equals some value. And the parameter could either be the mean or the population proportion in this chapter, and then the value is going to be given. where you'll need to calculate it. The null hypothesis is assumed to be true until we have evidence to support the contrary. We seek evidence that supports the statement in the alternative hypothesis. So we're trying to find evidence that's actually going to lead us to our alternative hypothesis, but that may or may not happen. So let's go ahead and look back at these exact same examples, and let's write the null and the alternative hypothesis and state whether it's two-tailed, left-tailed, or right-tailed. So let's start with A, which is in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. Okay, so the hypothesis is going to deal with, like we talked about, a population proportion P, okay, because we're talking about the percentage of American adults who fit some kind of characteristic. If the percentage participating in charity work is no different than in 2008, that means that it's going to still be 0.62. So we would form our null hypothesis by saying that P equals 0.62. So this is our parameter equal to some value, which in this case is our 0.62 from above. Now, read very carefully what the initial thing said. It said a researcher believes that this percentage is different today. So the researcher has kind of no indication as to whether it's less than or more than, just different. So this is going to be a two-tailed test where you have your null hypothesis as P equals 0.62 and your alternative hypothesis as P not equal to 0.62. Okay, let's look at this one here. According to a study published in March 2006, the mean length of a phone call on a cell phone was 3.25 minutes, and then a researcher believes that this has increased since then. So the null hypothesis is going to deal with the population mean, mu, and, well, both hypotheses are, because that's what we're looking at. We're looking at a mean. And if it's no different than in 2006, then the mean length of a phone call is still going to be 3.25 minutes. So we would say that the null hypothesis is that mu equals 3.25. And then if you read the original wording, it says a researcher believes that the mean length of a cell call has increased since then. So this is going to be a right-tailed test where our alternative hypothesis is that mu is greater than 3.25 because we think that the mean length of a phone call has increased. Now, looking at this example, this was our standard deviation example. They were using an old manufacturing process, and the standard deviation was 0.23. And this new, better equipment has led the quality control manager to think that the standard deviation has actually decreased, so that it's become more consistent. So our null hypothesis is going to be that the standard deviation is going to be equal to 0.23. Because if it's not changed, then it would still just be equal to 0.23. But the alternative is going to be a left-tailed test because we think that it has decreased. So we think that sigma is actually less than 0.23. So that's going to be a left-tailed test for our alternative hypothesis. Okay. Objective 2 is to be able to explain the types of errors that we can make. So there are 4 basic outcomes that can happen in a hypothesis test. So we can reject the null hypothesis when the alternative hypothesis is true, which would be a good thing to do. That would be a correct decision. If the alternative hypothesis is true, then we want to go ahead and reject the null hypothesis. We could also fail to reject the null hypothesis when the null hypothesis is true, which is also good. We don't want to reject the null hypothesis if it's true. Now, one thing we could do is we could reject the null hypothesis when it actually is true. That would be an incorrect decision, and that is called a type 1 error. And then we could fail to reject the null hypothesis when the alternative hypothesis is actually true, and that would be a type 2 error. So let's talk about in these situations what a type 1 and a type 2 error might be. So if we look back, you already know this charity work example. A type 1 error would mean that the researcher concludes that P is not equal to 0.62, when actually the true proportion of Americans who participated in some form of charity work is still 62%. So that would be a type 1 error. A type 2 error would mean that the sample evidence led us to believe that the current percentage has stayed at 62%, when in fact it's something different than 62%. Now if we look at this one, the phone call one, a type 1 error would mean that we would conclude that the alternative is true, that mu is greater than 3.25, when actually the actual call length of a cell phone is still 3.25 minutes. And then a type 2 error would occur if the researcher fails to reject the hypothesis that the mean length of a phone call is 3.25 minutes, when in fact it is actually longer than 3.25 minutes. So we have two Greek letters that we typically use. Alpha normally is going to indicate the probability of a type 1 error. So that's the probability of rejecting H naught when H naught is actually true. And then beta is going to be the probability of a type 2 error, which is the probability of not rejecting H naught when H1 is true. So the probability of making a type 1 error alpha is chosen always by the researcher before the sample data is actually collected. And then another word for alpha is the level of significance. And that's just the probability of making a type 1 error. Now, typically, you choose alpha based on how bad, how relatively not good it would be to make a type 1 error. Now, one thing to kind of note, though, is that as the probability of type 1 error increases, the probability of a type 2 error decreases. So it's kind of like a balancing act. If one goes up, the other one goes down. So the whole goal is to kind of balance the two and decide what types of errors you're willing to deal with, because you can never completely eradicate the error. Okay, now objective 3 is to actually be able to state conclusions to hypothesis tests. So before we actually perform any hypothesis tests ourselves, we want to make sure that we know how to state the conclusions. So one kind of word of warning here is that we never accept the null hypothesis, because without actually having access to the entire population, we don't really know the exact value of the parameter stated in the null. Rather, we say that we do not reject the null hypothesis, or we fail to reject the null hypothesis. Basically, it's kind of like the same thing in the court system. We never actually declare a defendant innocent, but instead we just say that the defendant is not guilty. So let's look at this right here. We have, again, our cell phone with 3.25 minutes. A researcher believes that it's increased. So let's suppose that the sample evidence indicates that the null hypothesis should be rejected. So if we want to reject the null hypothesis, we would say that there is sufficient evidence to conclude that the mean length of a phone call on a cell phone is greater than 3.25 minutes. So you would say that there is sufficient evidence to conclude that. And then for part B, if we decide that it should not be rejected, we would say that there is insufficient or there is not sufficient evidence to conclude that the mean length of a phone call on a cell phone is greater than 3.25 minutes. Or in other words, you could say that the sample evidence is consistent with the mean call length equaling 3.25 minutes. Okay, so now in section 10.2, we're actually going to perform some hypothesis tests for proportions. So we're going to start with population proportion, and then in 10.3, we're going to do the same thing for population means. So 10.1 was just meant to kind of introduce you guys to hypothesis testing so that you can understand the purpose, how to actually set one up, and then how to actually draw conclusions. So objective 1 is to just explain the logic of hypothesis testing. So let's look at this example here. A researcher obtains a sample of 1,000 people and finds that 534 are in favor of the banning of cell phone use while driving. So our p hat is going to be 534 divided by 1,000. So we want to know if this suggests that more than 50% of people favor the policy, or would it be possible that the actual proportion of registered voters who favors the policy is some proportion less than 0.5, and we just kind of happen to survey a majority in favor of the policy. So would it be, maybe we could say, unusual to obtain a sample proportion of 0.534 or higher from a population whose actual proportion is 0.5? So what is convincing or statistically significant evidence? So when observed results are unlikely under the assumption of the null hypothesis, we say that the results are statistically significant. So when results are found to be statistically significant, we go ahead and we reject the null hypothesis. So To determine if our 0.534 is actually statistically significant, we go ahead and we build a probability model, which is something that you're used to doing from previous chapters. So n times p times 1 minus p, if we go ahead and check that, it ends up being 250, which is obviously greater than 10, so that's good. And then the sample size is only 10 or 1,000, which is sufficiently smaller than the population, so there's no issues with having dependent data. So we can use the normal model to describe the variability in p hat. The mean is going to just be 0.5, and then the standard deviation is going to be found by taking 0.5 times 1 minus 0.5 divided by 1,000, and then taking the square root of that. So we're taking the values from our null hypothesis there, which if you do this in your calculator, you get 0.016 for that value. So we have a sampling distribution of our sample proportion. We have 0.5 right here. So what we're going to use in this case is the p-value approach. Now there are kind of two approaches. There's a classical approach and a p-value approach. And then you can also use, on your homework anyway, you can use StatCrunch in order to actually figure out the p-values as well. So you can use a technology approach in addition to these. So what we can do is we can determine how likely it actually is to obtain a sample proportion of 0.534 or higher when the actual population proportion is 0.5. And then if the sample is very unlikely or unusual, we have evidence against the statement in the null hypothesis. Otherwise, we don't really have sufficient evidence to say. So we're going to compute a probability. So all we have to do is find the probability of getting p hat greater than 0.534, okay? And this is just using the normal model. So this is just a typical z-score type of question. So all you do is you calculate z, you take what you're interested in, which is your 0.534, and you subtract your 0.5 from your null hypothesis, and then you divide by that standard deviation that we had already calculated. And when you do that, you get 2.15 as your value. So really what you're finding is you're finding the probability that z is greater than 2.15. And if you look this up on your table, if you're using the actual table, you're going to have to do 1 minus the table value since you have a greater than or a right-tailed test. And you should get 0.0158, or you can use technology to get this as well. So the value of 0.0158 is actually called our p-value. So 0.0158 is about equal to 0.02 or 2%. So that means that only 2 samples in 100 are going to give a sample proportion as high or higher than the one we obtained if the population proportion really is 0.5. So because these results are statistically, are unusual, we take this as evidence against the null hypothesis. So anytime you have something less than about 5%, we would call it unusual. Now, with the p-value approach, you already have an alpha set. Okay, we talked about alpha, the type 1 error, probability of getting a type 1 error. So if the probability of getting your sample proportion is as extreme or more extreme than the one obtained is small, then you're going to go ahead and reject the null hypothesis, okay? So we're always kind of assuming that the null hypothesis is true, and then we're figuring out the probability of getting a sample proportion that is as extreme or more extreme than the one that we obtained. So if that happens, then you're going to reject the null hypothesis if you have a very small value. So objective 2 is to actually test the hypothesis. So it's important that you remember how to find p hat, okay? It's just going to be x over n, where x is the number of individuals in the sample with some specified characteristic, and n is going to be the sample size. And then the sampling distribution of p hat is going to be approximately normal, with mu of p hat equal to p, and then the standard deviation given by this formula here, same as before. And then you know that it has to be a simple random sample, n times p times 1 minus p has to at least be 10, and the sampled values have to be independent of one another, meaning that it has to be less than about 5% of your population. So in order to actually test this, we have to have these things be true, and then we set up our null and our alternative hypotheses. So you'll notice the null hypothesis is the same everywhere, p equals p naught. P naught is just the assumed value of your population proportion. And then we have a two-tailed test, p not equal to, a left-tailed, which is p less than, and a right-tailed, which is p greater than. And then you go ahead and you select your level of significance alpha based on kind of the seriousness of making a type 1 error. You compute your test statistic, which is given by just your z-score formula, what you're interested in minus your mean divided by your standard deviation. And then you go ahead and use table 5 to estimate the p-value, or you can use technology. Okay, and this can be done using a graphing calculator, Excel, StatCrunch, and those tutorials are all given in a step-by-step instruction in the actual textbook. Now, if your p-value is less than your alpha value, then you reject the null hypothesis, and then you go ahead and state a conclusion, which normally starts with either there is sufficient evidence or there is not sufficient evidence. So if we look at this example, in 1997, 47% of Americans said that they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2007 poll of 1,010 adults nationwide, 525 of them stated that they did not trust the media. At the alpha equals 0.05 level of significance, is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997? So first, what we're trying to figure out is if p is greater than 0.46. So if we want to test this, we have to make sure that it fits the requirements. It's a simple random sample, which is good. And then taking n times p times 1 minus p gives us 250.8, which is greater than 10. Oops. And the sample size is less than 5% of the population size, so we can assume independence. So the first step is to set up your null and your alternative. So the null hypothesis, and that's going to be the statement of no change, is just going to be that p equals 0.46. The alternative is going to be that p is greater than 0.46. The level of significance is going to be 0.05. It's kind of a typical level of significance, although all of the homework questions, they always give you the level that you're looking for. The sample proportion is going to be given as 525 people who stated that characteristic out of the 1,010, which gives you 0.52. So to actually calculate the test statistic, we take what we're interested in, which is our 0.52, and we subtract the null hypothesis value, which is 0.46, and divide by the standard deviation, which uses the null hypothesis value of 0.46 times 1 minus 0.46 over 1,010, square root of that, and we get 3.83. Now, this is going to be a right-tailed test, so if we look up the probability that z is greater than 3.83, it's going to be almost zero. It's basically off the charts almost. This p-value is definitely going to be less than the level of significance, so we're going to go ahead and reject the null hypothesis. So we can say that there is sufficient evidence at the alpha equals 0.05 level of significance to conclude that the percentage of Americans that do not trust the media to report fully and accurately has in fact increased since 1997. So since our p-value is less than alpha, we say that there is sufficient evidence. Okay, now let's look at section 10.3, which talks about hypothesis tests for a population mean. So objective 1 is to actually test a hypothesis about a mean. So in order to do this, we need to use something called the t-distribution instead of the z-distribution. So when we replace sigma with s, we need to use this formula right here. So we take x bar minus mu divided by s over square root of n. And this is going to follow the student's t-distribution with n minus 1 degrees of freedom. Now, the reason that we do this is because we don't actually have a population standard deviation that's known for population means typically. So since we don't know what the population standard deviation is, we have to use the sample standard deviation in order to actually do this. So back when I think his name was Gossett, he was working for Guinness Brewery. He was doing some statistical analyses for them. This is way, way back. And he invented this distribution in order to help him solve this problem of not knowing the population standard deviation. So he invented this and he couldn't put it in his own name, so he just called it student's t-distribution, and that's where it came from. It works very well. The t-distribution is very similar to z. It has some differences that you'll see if you look in your textbook. I think it talks about them. I'm not sure if I have them on the slides coming up here, but there are some nice graphical representations in your textbook that does go through those differences. So in order to test a hypothesis regarding the population mean, we're going to use the following steps. Provided that we have simple random sampling, And then one of two things has to either be true. It can either have no outliers and the population comes from a sample which is already normally distributed, or the sample size has to be large. So the population can already be normally distributed and small, or the sample size can be large, one of the two. And then the sampled values are independent of one another. So again, small kind of sample size that's less than 5% of your population. It doesn't need to be small, but it needs to be less than 5%. Okay, so we're not going to go through every single piece of this because this looks exactly the same as our proportions, except we have mu's instead of p's. So null hypothesis is always mu equals mu naught, and then left-tailed is less than, right-tailed is greater than, and two-tailed is not equal to. We select a level of significance, again, based on the seriousness of making a type 1 error, so it's the same second step. We compute a test statistic, which looks a lot like our z-score, except it's a t value. So we take x bar minus mu over s over square root of n. And then we go ahead and look it up on our table. And we have a two-tailed test again, left-tailed or right-tailed, or you can use technology to look up these values as well. So you could use either your TI-83, 84, or Minitab, Excel, StatCrunch. Those instructions are all given in the textbook. Now we make our conclusions the same way. So if our p-value is less than alpha, we reject the null hypothesis. Then we state a conclusion. And one thing to kind of note is that the procedure is robust, which means that minor departures from normality is not going to really adversely affect the results of the test. However, if we have small samples and we have outliers, the procedure should not be used. Okay, so let's look at an example here where we have a population mean and a large sample. So assume that the resting metabolic rate of healthy males in complete silence is 5,710, I think it's kilojoules per day. Researchers measured the RMR of 45 healthy males who were listening to calm classical music and found their mean RMR to be 5708.07 with a standard deviation of 992.05. So at the alpha equals 0.05 level of significance, we want to know if there is evidence to conclude that the mean RMR of males listening to calm classical music is different than 5710. So we assume that the RMR of healthy males is 5710 per day. This is going to be a two-tailed test since we're interested in determining if it's any different. So there was no indication whether we thought it was less than or greater than, so just different. And then our sample size is quite large, so we're going to go ahead and follow the steps for testing a hypothesis about a population mean for large samples. So our null hypothesis is going to be that mu equals 5710, and our alternative is going to be that mu is not equal to 5710, since we just want to decide if they're different or not. Okay. Now level of significance is going to be alpha equals 0.05. Our sample mean was 5708.07, and the sample standard deviation was 992.05. So we just have to calculate our test statistic by taking what we're interested in, which was our sample mean, okay, our 5708.07, and subtracting the mean from our null hypothesis, which was 5710, and then dividing that by the 992.05 over the square root of 45. And we should get a test statistic of negative 0.013. So since this is a two-tailed test, the p-value is going to be the area under the t distribution with n minus 1, which is just 45 minus 1, or 44 degrees of freedom. And we're looking to the left of negative t of 0.025, which is equal to negative 0.013, and to the right of t 0.025, which is going to be positive 0.013. So our p-value is going to be 2 times the probability that t is greater than 0.013 because of the fact that we have symmetry. So we know that 0.5 is going to be less than our p-value, but that's kind of the only restriction that we're going to have on that. You want to make sure you're looking at your t distribution table, which I believe is after z in terms of the appendix. Now, since our p-value is greater than the level of significance, so 0.05 is actually less than 0.5, or we could say that 0.5 is greater than 0.05, we're going to fail to reject the null hypothesis. So we would say that there is not sufficient evidence at the alpha equals 0.05 level of significance to conclude that the mean RMR of males listening to calm classical music differs from 5710. Okay, objective 2 is about understanding the difference between practical and statistical significance. So when a large sample size is used in hypothesis testing, the results might end up being statistically significant, even though there is no actual practical significance. So practical significance kind of refers to the idea that basically, even though small differences between a statistic and a parameter might be statistically significant, the difference might not be large enough to cause any concern or actually be considered important. So let's look at this example here. So in 2003, the average age of a mother at the time of her first childbirth was 25.2. To determine if the average age has increased, a random sample of 1,200 mothers is taken and is found to have a sample mean of 25.5 with a standard deviation of 4.8. And we're going to use alpha equals 0.05. So what we're testing is mu equals 25.2 versus mu greater than 25.2. We have a level of significance of 0.05. So we take our t statistic, we calculate it as 25.5, which is our sample mean, minus 25.2 divided by the sample standard deviation, which was 4.8 over the square root of 1,200, because this was our sample size, and we get 2.17. Now this is a right-tailed test. The critical value is going to be alpha equals 0.05, and we have 1,199 degrees of freedom. And what we're going to get from table 6 is that we have a p-value somewhere between 0.001 and 0.005. So the p-value is much less than alpha, so we're going to reject the null hypothesis. So we would say that there is sufficient evidence at the alpha equals 0.05 level to conclude that the mean age of a mother at the time of her first childbirth is greater than 25.2. But if you think about what we actually obtained, we're really comparing the difference between 25.5 and 25.2. This is really not practically significant in terms of age difference, someone who's 25.2 years old and 25.5 years old. So even though the difference is significant, it's not really practical in this case. So this is kind of something that can happen with large sample sizes. So large sample sizes can often lead to statistically significant results, even though there is no difference between the statistic and parameter to be considered practically significant. Now in section 10.4, there's not actually anything new, but what I want to just go through in this section is kind of just recap what we had done. So if you were asked to compare a population proportion to some other value from a sample, you need n times p naught times 1 minus p naught to be at least 10, and you can use the normal distribution with your z-score calculated as p hat minus p naught over the square root of p naught times 1 minus p naught over n, and then your p hat is calculated as x over n. Sometimes this is actually given this way, or sometimes you need to actually calculate how many people from your sample have the given characteristic. Now, if you have a mean, provided that either your sample size is large, meaning at least 30, or if the population is already normally distributed, you're going to use the t distribution with n minus 1 degrees of freedom. And you're going to have t naught equals x bar, which is your sample mean, minus mu naught over s over square root of n, where s is your sample standard deviation and n is your sample size. Now, you can also do a hypothesis test for variance or standard deviation, but we're not doing that in this class, so I'm not going to go ahead and cover that. So that is it for this week. Thank you so much for watching, and I hope you have a great week.